will be finally mimicking the functioning of human brain or the biological neural network. The definition of neural network can be considered as an information processing model which is inspired by the way biological nervous system works, that is the brain process the information. And ANN is composed of large number of highly interconnected processing elements called neuron, and they work in unison to solve a specific problem. And it is specifically configured or designed for particular applications such as pattern recognition, data classification through a learning process. So, a very good definitions by the book Siemens Hakin as the author of the book. Artificial neural network is a massively parallel distributed processor that has a natural propensity of storing experimental knowledge and making it available for use. And it resembles the brain in two respects. First, the network through a learning process acquires knowledge. Similar way as we know that our human brain, it develops in due course of time, starting from our childhood till we are adult, or till we used to learn from examples or set of experiences. The similar way artificial neural network will work. And how it will store the knowledge. So there is an interneuron connection strength known as synaptic weights. This is used to store the knowledge that we acquire during different learning experiences. So the fundamental of neural network is basically the main unit known as neuron, and they are biologically inspired by human brain to perform the various complex tasks. And this neuron is also sometimes referred as node or a processing unit. So why we need to know about artificial neural network? The main curiosity behind this is that various problems, particularly of pattern recognitions or of face recognitions, like for example, we want to recognize a face of an old friend whom we know very well. For past few years, we haven't got in touch with, and now we have been presented the image of the friend in an embedded form, so we want to recognize it. We can do it very easily, but the same task is actually very hard to apply for the computer to do. So how conventional, you can say, the soft computing differs from hard computing, that is the main task herein. Using artificial neural network, we can easily perform various pattern recognition, content addressable recall, approximate reasonings, and common sense reasoning, like we want to drive or play piano or any uh, play like baseball, football. So how to react with the situations that can be easily handled by our human brain. A similar way, we want to make a model of artificial neuron which can work in the similar way as human works, but that for a particular specific problem. We human can simultaneously do many examples or many tasks simultaneously, but the task done by artificial neural network will be one at a time. It is for which it has been specifically designed. So starting with how a human brain works. So human brain consists of large number of connected elements called as neurons, and the quantity of neurons that are available in our human brain are approximately 10 raised to 11. So, and these neurons are highly interconnected to each other, and usually there are 10 raised to 4 connections per element, and these connections are known as synapse. This is the structure of human brain. You can see it here. This is known as one neuron, which consists of a cell body. This is soma, and the tree like structures coming out of this cell body, they are known as dendrites. At the end of the dendrites, the bug like structure which is connecting to other axon, that is known as synapse. This is used to store the knowledge, and the actual output is taken from the this large connection known as axon. So axon gives you an output, dendrites takes the input, the synapse gives the knowledge to them, or you can say the strength or the weighted energy is given by this synapse. In this way, human brain works. So now herein we will be seeing somewhat more related to how this human brain works. So herein every neuron consists of a cell body and as an axon and many dendrites. So these dendrites will be taking the inputs from the external environment. So they can be in two states, either in firing states or in rest state. So whenever the external stimulus is presented to the human brain, these dendrites will be in firing states, otherwise they will be in rest state. When neuron fires, then whatever total incoming stimulus is there, it is aggregated here in nucleus, and it is further compared with a threshold function. And if it exceeds the total incoming stimulus, if it exceeds the threshold functions, then a high signal, or you can say the response signal, that is coming out by the extend human brain to different parts of the body according to the situations that has been the human brain has been subjected to. So here in this synapse is what this bulb-like structure, which is a thin gap between an axon of one neuron and dendrite of the another neuron. Herein signal exchange will takes place, and it gives you the strength or efficiency for storing the knowledge. So we understand that how a biological neural network or a human brain works. So now we want to mimic this biological neural network by an artificial neural network. So what we will be requiring, we should also have a set of nodes similar to the neurons in human brain. Sorry, but there was certain interruption in the network. So, to consider the comparison of ANN and biological neural network, in biological neural network, there is a cell body which represents the nodes. Each inputs in neural network is considered to be the dendrites, which has a signal firing mechanism in biological neural network. There is an output in artificial neural network, which is related with the axon in biological neural network, which is the connection strength between two neurons, you can say. Then there is a node function in ANN, whereas in biological neural network, there will be the soma or the nucleus which will perform this node function. And the connection strength in neural network known as weights. And in biological neural network, it will be considered as the synaptic strength or the synapse. Here in biological neural network or artificial neural network, we mainly concept is that there will be large number of neurons which are highly interconnected and working in parallel for and in unison for local computation at neuron level, and they will achieve a global result and overall interaction at the network level. And patterns, they are directed in such a way that individual nodes only in context of a pattern, and they will be fault tolerant. That is, if any of the neurons or interconnection strength they get damaged during course of time in that so performance of the overall neural network will not degrade abruptly, whereas it will be degraded gracefully, so they are considered to be fault tolerant. And learning and adaptation, that plays very important role in this case. So starting with the history of neural network, the foremost model is known as Pix and Mukluk model, which was developed in the year 1943. So this particular model can solve all Boolean operations very easily, and these are basically the OR gate, NAND gate, NOT gate, any gate particularly which is linearly separable. Only the XOR gate, which is non-linearly separable problem, cannot be solved using this particular model. Then in 1949, there was a Hebbian rule given by the scientist Hebb, and this can also work both in supervised and unsupervised learning. To update the values of weights and biases, this rule is used. Then in early 50s to 60s, the perceptron network, which was developed by the scientist Rosenblatt in the year 1958, this rule, and also he gave the perceptron learning rule to update the values of weights and biases for a particular problem statement, and also the convergence theorem that the rule will converge to the final weights and biases if it is presented and learning is done in the manner being defined by this rule. Then there was a scientist known as Widow and Hoff. So he gave the gradient descent rule, which is the learning rule for differentiable unit. And in late 1960s, there was a scientist known as Minsky. He particularly raised a serious problem with the perceptron model, which says that this perceptron model is a single layer network, so it can only represent the linearly separable problem, and it cannot solve the non-linearly separable problems such as XOR. So there was a major setback on the further improvement or development of learning rule for neural network for till late 1970. Then particularly the problem was solved by the introduction of backpropagation learning algorithm for the multi-layer neural network, which can work for both non-linear and differentiable node functions. And also another Hopfield network and Boltzmann machines were developed, and different unsupervised learning algorithms were also discovered. So in this way, we are able to see the neural network is gaining more popularity day by day with the introduction of different deep learning algorithm as well. So I will tell you how the McCall-Spit model works. It basically takes different inputs, apply a weight value to them, and aggregation of the weighted inputs is done at the network side, and then compared with a function known as activation functions to give an output. So these weights can be positive. So if they are positive, they are considered to be exhibitory, and if the weights is negative, they are considered to be inhibitory. In few books, you can find the weight value positive is considered to be simple weights, whereas negative values is considered to be bias. So bias is usually to offset the decision boundary with respect to origin. So this particular model can solve the various Boolean functions like AND, OR, NOT, NOR, and NAND, except XOR. So, in definition, what is an artificial neuron? A neuron is a processing element that takes a number of inputs, weights them, sums them up, and uses the result as an argument for a single value function known as activation function. You can see it like this. Different inputs are taken, we multiply them with weights, aggregation is done, apply this net input to the activation function to get an output. So that was a structure of a simple neural network. But actually, to solve a realistic problem, we will be using multi-layer neural network. What is multi-layer neural network? Multi-layer network consists of more than one hidden layers, and here you can see that this is the input layer and this is the hidden layer, and this you get an output. The input of the first layer is taken as out. You can say here output of the first layer is taken as input to the second layer, so that is considered to be a multi-layer network, and it also consists of all those components that were described earlier. You can see here there is a bias term which is usually considered to be a negative offset. Now, what are activation functions? These activation functions are generally non-linear, and linear functions, they are limited because the output is simply proportional to the input. This is pure line functions. Whatever will be the net input, that is same as an output. So that is a pure line function. Then there are certain threshold functions. This is considered to be symmetrical hard limb function, because for n value, that is the net input, if it is greater than 0, then output is high. If net input is less than 0, output is -1. Then there are functions like settling, tangent sigmoid, log sigmoid, radial basis functions. Among these, the choice of transfer functions is dependent upon the designer of the neural network based on the variations of the input and output, in what range they have been chosen. So different MATLAB functions that can be used for the different activation functions, they are given in these slides. Particularly the tangent sigmoid and log sigmoid, these are the functions which are most widely used for problem statement, particularly which has the variations in the range of plus minus infinity as the input value. There are different kinds of neural network, as I told. It can be categorized into two categories as feed forward network and feedback network. They are also known as recurrent network. Under feed forward network, they can be considered as supervised neural network and unsupervised neural network. Then under supervised neural network, they can be single layered or multi-layered supervised network. Under single layer, they can be single input, multi-input. So how they are categorized, you can see it here. This is considered to be single input neuron, wherein only one input and one output is taken up. Then there are multiple input and still one output. So multiple input, one neuron, this is the case. Then there will be multiple input as well as multiple output neuron. This is the case. S number of outputs are taken, R number of inputs are taken, multiplied by weights, aggregated, and also added the bias value to get the net input, applied it to activation function, get the output. And abbreviated notations for the multi-layer network is shown in here, which shows the size of the matrices of weights, biases, and the input and output. If I'm not clear, or anytime if you have any doubt, you can interrupt me in between the audience participants, please. Okay, so this is the multi-layer network. You can see it here. There are R number of inputs and s raised to 3 number of outputs. So these will be actually the number of pairs, labeled target pairs available with you. And in this neural network, how it will work, the output of the first layer will act as input to the second layer. Similarly, output of second layer will act as input to the third layer, and final output will be taken from the last layer. So you can see here in how the function will be working. And if multi-layer network is there, so they will be large number of neurons, they will be interconnected to each other. So the complexity of the multi-layer neural network is quite high, and usually the 3-layer network is a vast majorly used with say 20 to 30 number of neurons in the hidden layer to solve almost major problems of the engineering, different engineering fields. In abbreviated notations, this is the multi-layer neural network. I will not cover much details related to it. Now, how the multi-layer neural network training is done. What is the main concept behind learning? So that is explained herein. We have been provided an input and a label target values, input along with target values. So what we do with the say a random chosen number of neurons and hidden layers, initially we started, usually we start with a lower number and then we increase the number of neurons based on the error that we get between the actual output and the targeted value. If error is large, we increase the number of neurons in the neural network. If error is small, then we make retrain the network such that the and adjust the values of weights and biases to reduce the error between the target and actual output. So in this way it works. Usually it is done for multi-layer network using the backpropagation algorithm known as delta rule. Then in recurrent network, it's a feedback network where it output is given as feedback to the input side, and the first output is taken directly with certain delay as an same as an input, and then the output is taken as feedback. So such network is known as feedback network or recurrent network. D is delay herein. Say for timestamp 1 second. How does it work actually? What we need to do, neural network works in the way like this is an AND gate problem, and AND gate says that if any values of input is 0, so it will all are 0, 0, 0, 0, 1, 1, 0. So that will give you a 0 output, whereas if both the inputs are 1, then only you will get a high value. So this is the output. So you draw a decision boundary which separates the high pattern with the low pattern, such that at one side the high targeted input variables are available, and on the other side low target value, that is t equal to 0, are there, and weight matrix is decided such that it uh, resides in the high dimensional plane with high output, and it is usually perpendicular to the decision boundary. Decision boundary is the equation of W transpose P plus bias. Then when it is equated to 0, that gives the linear decision boundary equation. We can classify the patterns using this perceptron network by choosing the decision boundary such way it points the in divides the patterns into two different classes, and the weight vector chosen such that it points to the highest input patterns value. You can see it here. This is the value, and it is perpendicular to the decision boundary. Now, as I told, there is a limitation for the single layer feed forward network to solve the XOR problem. XOR problem says that OR problem can be easily classified. These are the three. OR gates means if any input is 1, it gives a high output, and only when 0, 0, it gives. So this is a simple decision boundary. But for XOR problem, which says that if any input, if it is 1, then it gives an high output, whereas if both are 0 or both are 1, it gives a 0 output. So this cannot be classified using single decision boundary. It requires multi-layer network. It requires two decision boundary, one here, and both should work in AND operation. When both are there, then only it can work. So that can be solved using multi-layer network. So in case of neural network learning process, usually supervised learning and other is the unsupervised learning. So in case of supervised learning, we present the network with a number of inputs and their corresponding target value, and they work in such a way to match the actual outputs with the desired one, and they in subsequent iterations during learning, they will reduce the error between these two, and if it reaches the set value or the goal set, then learning is stopped. So main idea behind the unsupervised learning is that there will be no target value assigned to any of the input data. So it will be non-labeled input patterns. We will not be knowing the output for the corresponding input data a priori, and usually you can consider it that there is no need of a teacher or a professor, and usually it is considered to be solving the data clustering problems. Network itself finds the correlation between the data, such as the Cohen network, which is the self-organizing feature map, SOM network. And in supervised learning, we get the desired response corresponding to the input level. So there is a teacher or a professor which provides you examples, teach the neural network how to fulfill the certain task in case of supervised learning. So starting in the learning process, we initialize the weights randomly. We present the network with the training samples and adjust the weights, check the behavior of the network or the stopping criteria. For each input patterns, we check for all patterns, you can say, whatever patterns they are available, we check the actual output value and the error between actual output and the proposed output and the targeted output that is taken up. If it is error is more, then weights and biases are adjusted, and the adjustment is done using this rule. This is known as the backpropagation learning rule. W nu is equal to W old plus a function h, which is of y, which is output, x is input, and e the error. In case of unsupervised learning, there will be no y, no targeted value. So only x and y will be presented to adjust the weight value in case of unsupervised learning rule. And finally, usually it is done in terms of breaking the total data set into three different parts: training data set, testing data set, and validation data set. Usually validation data set is required to measure the generalization capacity of the trained neural network for unforeseen patterns. Stopping algorithms, how when the network should stop the learning. So there are different criteria, particularly when the error goal is reached, when the total number of iterations is reached. These are the two stopping criteria. Or also when the error in the validation data set is more, then the stop error is training is stopped. So the backbone of neural network is the backpropagation algorithm, you can say, and it is used for training the multi-layer feed-forward network, and it uses the delta rule for updating the weight value. What are the advantages of neural network? So neural network is adaptive, it is self-organized, it can work in real time, it is fault tolerant, so and also noise immunity and robust. These are the various advantages. It is applied in different fields, you can say: face recognition, handwriting recognition, time series predictions, process control, pattern association, function approximation, parameter estimations. In various fields, neural network has been already applied, and particularly you can say real world problems like air traffic control, stock market predictions, data mining, eco patterns, traffic for weather predictions, fraud detections. There are many medical diagnosis. So now herein I will be discussing about the application of AI and machine learning in the area of power system. So a brief introduction about power system. Power system consists of the generating units, then the step up transformer or the generating transformer, which is used to step up the voltage to a higher value to reduce the overall losses during transmission or sub transmission, and then it is stepped down at the end to be finally used by the loads. Usually loads are connected either at 11 kV or at the household loads, which are considered to be at connected at either the three phase 400 volts or 220 volts. So this was the basic power system network. Now it is being modified, known as by the smart grid system or the microgrid system. So what is microgrid? Microgrid is defined as a decentralized group of electricity sources and loads that normally operates in connection to and synchronous with the traditional wide area synchronous grid, and they can also work in disconnected mode known as islanded mode and function autonomously as a physical or economic condition dictates. So this is known as microgrid. You can see here microgrid consists of various renewable energy generating sources as well as the thermal state generating sources and the transmission systems. So with a point of common coupling, they can be operating in utility grid connected mode or in the islanded mode. And what is smart grid? As per Electric Power Research Institute, smart grid is defined as the grid which incorporates the information and communication technology into every aspects of electricity generation, its delivery, consumption, in order to minimize the environmental impact and enhance the market, improve the reliability and services, and finally reduce the cost and improve the overall efficiency of the grid system. So that is known as a smart grid. So you can see here in whereas the conventional power plants like thermal, nuclear or hydraulic power generations, then the renewable energy sources like solar plant, wind power, so they are there, and the transmission systems are interconnected. So this is a smart grid, and various loads like household load or factory load, various electric vehicles or cities, urban areas, so all these are considered to be loads. These are your generating stations. They here in the communication between the grid and the loads as well as generating stations will be set up by the information processing systems and the communication infrastructure, which considered it to be a smart grid. Now, there is a term known as distributed generation. So, distributed generation is defined by IEEE as the generation of electricity by facilities that are sufficiently smaller than the central generating plants like thermal or nuclear power plants, and they allow the interconnection of these generations at all points in the systems, usually at the distribution levels. So they will be connected at the low voltage value because of the low volume in productions and low cost driven as compared to the enormous nuclear or thermal generators. They are gaining increasing popularity because of the cleaner and sustainable energy provided by the distributed generating sources, particularly by photovoltaic cells, PV array, wind turbines, or fuel cell, etc. So there can be different types of renewable energy sources by hydro, solar, wind, tidal, geothermal, or biomass. Now what will happen if we integrate these into the power system network? And we all know that in India the potential of renewable energy sources is quite high, and we have particularly renewable energy sources that are present in Rajasthan, Gujarat, Maharashtra, Madhya Pradesh, Jammu Kashmir, and other states. If we combine, that is 16%. So we have quite good potential of generation through renewable energy sources. And if you talk about the solar PV capacity that has been added, total capacity in the year 2021, we are third among the world in the installed capacity of solar PV. And if we talk about the this is that we have added into 2021, and if we talk about the cumulative solar capacity, total capacity, so we are fifth among the world different countries. And if we talk about the wind capacity, so you can see here in 2021 we have added, this color is this, only this much of portion of wind total capacity that has been added by India. And total among the total cumulative capacities, we lie in fourth among the different countries around the world. There are different onshores large wind farms available. You can see particularly the Mupandal wind farms at southern India, which is of capacity of 1500 megawatt. And there is Jaisalmer wind park, it's in west side, it is of 1064 megawatt. There are many others. So this particular the wind farms of Tamil Nadu that I told, it is the largest capacity Mupandal wind farm. And among the total installed capacity of wind power, we are fourth in the world. There are also different hydropower plants. The biggest hydropower plants is present in Brazil of 12,000 megawatt, and these hydro plants can be classified into different categories based on the capacities. You can see that up to 15 megawatt they are considered to be small hydropower plants, and if they lie between 1 to 5 megawatt they are considered to be mini hydro plants, and if they are less than 1 megawatt they are considered to be micro, and if they are less than 100 kilowatt they are considered to be nano hydro plants. Particularly ecological considerations are there, that these power plants can only be situated or built up in the area where we have the large water resource, the river available. So we need to construct a dam, and then these power plants can be constructed. Now with integration of different renewable energy sources where we can integrate into the grid, that is the main task. So as I told that basically the grid, it is at different voltage levels. So 230 to 415 volts, this is the voltage level that is available, considered to be the low voltage distribution grids, which is usually the residential loads, okay, at the lighting load and fan load. So herein we can integrate the photovoltaic panels. You all know that at the rooftop we can install the photovoltaic panels, so we can integrate this PV type of DGs at low voltage grid. Then coming on to the small scale hydro power plants or biomass based or tidal based power plants, or small combined heat power plants, they can be integrated at medium voltage levels between 11 to 66 kV. Then there are large industrial captive hydropower plants, and combined heat power plants, and large scale hydro offshore wind parks, which can be integrated into a voltage level between 66 to 132 kV, which is considered to be high voltage distribution grid. Then various other power plants, particularly which are conventional one like nuclear thermal power plants, they are integrated at a voltage level greater than 132 kV. So you can see here in that DGs basically they are integrated in the distribution grid at low voltage levels. These DGs can be either PV based, solar based, hydro based, or wind based. Now what happens when you integrate the DGs to the distribution networks? So the major change that occurs is the power level. When the microgrid is transited from grid connected mode to the islanded mode, islanded mode itself says that what we are disconnected from the utility grid and we are operating only for the loads which are locally connected with respect to the DG. Okay, then when different types of DGs have different fault contributions in islanded mode. In case if the inverter based DGs are there, then the fault current contributed is twice the inverter rated current. Whereas if there are synchronous based DGs or induction based DGs, then 4 to 10 times the fault current contribution is there in case of faults. So fault current level changes accordingly. We need to design the protection schemes for these microgrids, which should handle such variations in the fault current level. And if number of DGs that are connected at the present a particular time, if they vary, then also the fault level will change. Now another major problem, earlier the system was radial, that is the generating stations was situated at one end, and power was evacuated from generating stations through transmission line and distribution lines, and then finally given to the load. So the system was radial, there was no other source in between connected. But with integration of these DGs at various distribution level, the system is no more a radial one. So here bidirectional power flow takes place, and which causes the loss of coordinations of the overcurrent relays, which are usually installed for a radial power system network. Also with when these transmission or distribution systems are subjected to high impedance fault, nuisance tripping, or unplanned islanding, so these case causes protections issues in operations of distribution system. I am having sufficient time now, Deepak. Deepak, please Please, anybody say in between so that am I audible or I'm still connected or not? I should check it.
Yes, ma'am, you are audible.
Yes,
Okay.
madam,
You
you
are
are
audible, ma'am.
audible. You are
Okay.
audible.
Up till now, the concept that I have given to you all are very clear to all of you. Are you able to understand it?
Yes, madam.
Yes. Okay. So I will continue. So now, this is the development of the different protective relays. In 19th century, you can see here that the various power line carrier, distance relay, directional overcurrent relays, and differential relays, they were developed in this era. With the advent of computer in the 1970, then we went to move on with the development of rectifier, transistor, integrated circuits, and microprocessors. So different AI based techniques have been started in the year 1990 around the world, causing adaptive and traveling wave techniques in the year 1970s. Different with introduction of GPS in 1990, transient based, wide area based, and integrated and cloud big data. These are the new developments in the protective relaying schemes, which integrates the communication infrastructure to get the remote end data so as the wide area SCADA based systems can be implemented for protection. So what is wide area protection schemes? It utilizes the phasor measurement units. Phasor measurement units is basically a system, and you can say the measurement particularly of the voltage and current signals, and there is another term known as micro PMUs. So micro PMUs are usually installed at distribution levels, whereas normal PMUs, they are installed in transmission systems. Okay, and so that is only the difference between these two as per the voltage level that is being taken up. So these are basically communicating with the central level control centers using concentrators to get the information of the power flow, voltage, current, and angle, and accordingly the protection schemes utilize this information for protection of the transmission and the distribution systems. Now we are more focused to know what are the applications of AI in the power system network. So herein we will be seeing that economic load dispatch problems, particularly for operation of the generations and the distribution systems, and different load forecasting problems and optimization problems for generation schedulings. Then we need to limit the active and reactive power of the generators and the system reliability. We can have the control of voltage and frequency for system stability, and sizing and control of different flexible AC transmission system devices. Then we can have the fault diagnosis and power restoration management systems, and different demand size response and management systems, and ANN, particularly artificial neural network, machine learnings, they have been widely applied for the problem statement of protective relaying, particularly fault detection, fault classification, faulty phase identification, fault section identification, fault distance location. So all these have been successfully applied. So I will be discussing few of them with you in this particular slide. So starting with application of a neural network, particularly the modular artificial neural network for wide area monitoring and protection of a microgrid with our integrated with DGs. So this is the test system that we have chosen, which is a microgrid system as per IC standard 61850-7-420. You can see herein that there is total 6 PMUs placed, micro PMUs placed for each buses, and these are the line sections, and they are feeding different loads. You can see here L1, L3, and different DGs. There are 3 types of DGs connected here: DG1, DG2, DG3, and this is connected to the utility grid through main circuit breaker. If circuit breaker is open, so this operates in islanded mode, and if circuit breaker is closed, this operates in grid connected mode. So this is the concept. So what we need to do, we need to design the neural network to provide the fault detection in different line sections which are considered to be, say, between 1 to 3, line section is S13. Between bus 3 to bus 5, line section is S35. So fault is located in which of the sections, whether fault is present in the system, which type of fault is present in the system. All these tasks can be done using neural network. We'll see how. So starting with the measurements of voltages and currents at all the 6 buses. So, and this will be the synchronized measurement done through micro PMUs. Okay, synchronized measurement is necessary so that the we can have the at the same time stem the voltage and current signals at all buses are available with you. Then we apply the discrete Fourier transform to extract the fundamental component of voltage and currents at each bus. Then the first stage of neural network comes herein, which says that we need to know whether the system is operating in grid connected mode or islanded mode. That first need to be identified. So first neural network has been designed for this task. So if it gives you that the system is connected in grid connected mode, then further 3 modular neural networks are designed. First for fault detection, second for fault phase identification and fault classification, and third for faulty line section identifications. Similar way for the islanded mode also. So you can see that all tasks can be done, but with separate neural networks. So, and all neural networks are considered to be a modular neural network. So how it will be done? You can see here in grid connected mode or in islanded mode, we get a output for fault detection, the first one. So we take 6 inputs of each 3 voltage, 3 currents, so total 6 inputs, and there are 6 buses, so total 36 are the inputs. And then there are 2 hidden layers with 30 and 10 neurons in each for fault detection in grid connected mode. And you can see the transfer function that is used is tangent sigmoid, and then it gives you an output as fault detection, whether fault is there. If fault is there, output will be high 1. If fault is not there, output will be 0. Okay, so this is for grid connected mode. Similarly for the islanded mode, for islanded mode and grid connected mode, we have taken up and presented to an OR gate to get the final detection of fault, whether in grid or islanded mode of operation. Similar way for fault classification, we have 4 outputs, 3 for the 3 phases and 1 for the neutral. And for faulty section identification, there are 5 line sections, 5 outputs have been taken. So this way modular artificial neural network works. We need to train the neural network with a set of examples. Similar way a human brain works, we need to learn by having experiences and a set of examples in due course of our life. So similar way neural network needs to be first trained with a set of patterns. For that we need to simulate these faulty situations using power system analysis software like MATLAB, PSCAD. There are various other softwares also available like MyPower or Digilent software, or there are many others. You can see anyone can be used to create these faulty situations and extract the voltage and current samples on the selected test system grid that we have chosen. So herein we create faults on different line sections at different locations, different types of faults at varying fault resistance, at varying fault inception angles, at different operating modes, grid connected and islanding modes, all faulty situations. Then we need to also know that the system may be subjected to different dynamic situations. What are those? Change in the system loads, change in the switching of the DGs, whether switch in or switch out, that is they are connected or disconnected. Similarly, distribution lines, whether they are connected or disconnected, it may be for during maintenance purpose the lines are switched out. Okay, so starting with, once the network is sufficiently trained, we need to now check the performance of the trained network with unforeseen data set. So for that, what we create another test data set, wherein, say for example, we have created an double line to ground fault in the line section 3-4 at midpoint of the line section at 10 kilometer from bus, and at the time inception is 1.6. So what happens to this? So first foremost condition that we need to check is whether it is grid connected mode or islanded mode. You can see that grid connected mode gives you the high value 1, this 1 value. So it is operating in grid connected mode. So grid connected mode output of fault detector gives you the high signal. You can see here at 1.6 we incepted the fault, and the fault has been detected at after 12 milliseconds. This is in seconds, the time period. So it is 0.012 seconds, or you can consider it to be 12 millisecond. 12 millisecond is the fault detection time. Then fault classification or faulty phase identification. So the three phases A, B, C and grounds are there as the output. After 1.6, the fault of inception, you can see the corresponding faulty phases rises to a higher value as well as the ground, confirming that the presence of double line to ground fault in A, B and G. And which of the line section is faulty? So 5 line section among them, only line section 3, 4 becomes high, confirming that this line section is faulty. In this way we can work. Similarly, we can operate in islanded mode and check whether say at 19 kilometer in line section S12 we created a fault after 1.75 seconds. So after 1.753 seconds we get the fault detection, and now it is in grid connected mode ki jagah it is operating in islanded mode. You can see islanded mode value is high. First that is considered, and then fault is detected, classified, and line section is identified as 12. So here you can see the spikes in the other line sections, but that spikes die out in due course of time, whereas the actual faulty line sections gives you the high output throughout the simulation time. So that confirms the presence of fault in line section S12. Now what we need to check whether the system is not behaving as faulty for changing load conditions. That should be there. So for that we change the load, disconnect the load, or we add up the load. Any condition can be simulated, and we check whether fault is detected. No, output is 0. All outputs of classifier and line sections are 0, confirming that system is in healthy conditions. The system is subjected to load change, not the faulty. So herein we consider the modular artificial neural network, which uses the wide area measurements from the microgrid, and it is solving all protective relaying problems of fault detection, faulty phase classification, as well as faulty line section identifications. So herein we use modular artificial neural network for all these three protective relaying tasks. And herein what we can do, we not only detect the fault but also detect the fault type and faulty phases as well as faulty line section in both grid connected and islanded mode of operations. So this proves that centralized measurement schemes using wide area measurements is better as compared to the local bus measurements for protection of microgrid. So this confirms the first summary. Now we are moving on to the next one, which is the high impedance fault. What is the major beauty of high impedance fault is that in case of high impedance fault, the current is of intermittent, it has asymmetry in nature, it has build up in nature, you can see it rises up. So this type of faults particularly they are not detectable by the conventional overcurrent relay. So we need to design a separate schemes for detection of high impedance fault. So that has been taken herein. You can see here low impedance fault can be easily detected by the conventional scheme, but high impedance fault is not, because there is not a large variation in the output current. Okay. And similarly, capacitor switching, transformer energizing may also cause the change in the current. So all these are to be considered as non-faulty by the protective relaying scheme. Similarly, variations in the parameters of the DGs. Say for example, if it is a wind-based DGs and the wind speed changes from 7 meter per second to 15 meter per second. So how does the scheme will behave? If one DG is out, all other DGs are present. So how the scheme will behave? All these conditions should be considered as non-faulty. So herein we utilize a modified IEEE 13 bus system, and current signals are pre-processed using variational mode decomposition schemes, and then further support vector machine as the classifier has been used to classify whether the fault is present in the system or not. So this is the IEEE 13 bus test node system, and this is the relaying bus, and we created faults in these line sections, and it consists of various DGs, PV based DGs, wind based DGs, diesel generators, and battery storage based DGs, and this is the utility grid. We apply VMD algorithm here to extract the input features. You can see herein that this is the current signal and this is the fault point. Herein high impedance load has been switched, that causes the changes in the current, and we apply VMD. It gives three intrinsic mode functions, and using first intrinsic mode function, and then we calculate the single value decomposition scheme. You can see herein this gives you the signal of VMD SVD that is used as an input to the SVM classifier. SVM is the support vector machine, which gives the maps the original input space of feature vector into a linearly higher dimensional separable plane, and that using the dot products, and the generalization capability of this type of classifier is maximized by recognizing the hyperplane, and with the maximum separability. You can see here the separability is increased, and using the optimization problem, this is the decision boundary equation. W transpose x plus bias should be equal to -1. This is your main separating plane, and this is the hyperplane with maximum separability. All the patterns at one side of the hyperplane are classified as one class, and other are classified as the second class. So here it also requires the training patterns. So all those training patterns have been generated for low impedance, high impedance fault, and different switching events. Switching events are non-faulty events, and rather these two are faulty events. Then the proposed scheme is designed herein like this. We extract the current signal, apply the VMD and single value decomposition schemes, check it with a threshold as 5 per unit. If it is greater than threshold of 5 per units, then it is considered to be low impedance fault. If not, then it is further checked using support vector machine to identify whether it is a high impedance fault or not. If it is yes, then we issue the trip signal. If no, then we further consider whether it is a switching event or a non-faulty event. So if not, then we go to the original one. In this way, no trip signal is issued during switching or non-faulty events. So in case of low impedance fault, you can see that the proposed feature is well above the set threshold of 5, and it gives the trip signal for low impedance fault. But for high impedance fault, if you look to the current signal is not much increased. If you see, to identify whether fault is there, it is quite difficult for the operators. So, but proposed VMD SVD's feature vector is quite distinct from the non-faulty to the faulty one. So it gives the SVM is able to detect such type of fault correctly. Similarly, for high impedance fault under normal DG operations, with change in the irradiance level of the PV array from 700 watt per meter square to 1000 watt per meter square. Similarly, for change in speed from 15 meter per second to 7 meter per second, all that case are easily identified. For harmonic load switching, you can see here the value of the input feature is less than 5 set threshold value, so no trip signal is issued either in DG switching or in load switching. Similarly, for capacitor switching, it is less than the threshold set value, so no, or also for transformer energization, that can be easily identified at the, seeing the spikes in the current signals, but that does not affect the relaying operation. For reverse power flow, also the system works robust. Now, the choice of classifier, that also depends like which particular classifier we should use. So neural network, probabilistic neural network, and support vector machines, we have compared these three in terms of accuracy, dependability, security, sensibility, and safety features. So we can see that the SVM provides you higher efficiency of all these. Similarly, we investigated the noise. 30 dB noise is considered to be maximum. In that case also, we have the percentage of accuracy obtained between 99 to 97. So that is quite good in detecting the fault with presence of noise also. And further real-time validation of these schemes has been carried out using OpalRT simulator available in our lab, and it's a OpalRT 5600, and using a personal computer and the digital storage oscilloscope, we have shown the real-time operation of the proposed protective relaying scheme. You can see here in the current signals in this scope, and then this is the measured at the relaying point, this is at the incepted point, and then the trip signal issued by the circuit breaker that is shown here in, which is confirming that the presence of fault in the system. So real-time validation is done. Also, we have to compare the proposed scheme with the different works available in literatures, and we find that the proposed scheme is while working under different variations in DG, different switching events, classifying high impedance fault, low impedance fault, and detection time is good. So in this way, we confirm that the proposed scheme is outperforming over the existing schemes. So this is the summary. Herein we have improved solution using VMD and support vector machines to detect the high impedance fault and to distinguish them from the switching events in the distribution lines that has considered the presence of DGs, and this algorithm outperforms and discriminates the faults from different switching events. Test results evidence the accuracy in identification of HIF fault up to 99%, and the response time for low impedance fault was 16.67 millisecond, whereas for high impedance fault was 116.67 millisecond. And also the scheme has been validated in real time using OPAL-RT digital simulator for practical applicability. So this covers major portions. Now I am open for you all for different discussions. These are few of the references that you may check out for this. This is my Scopus profile, you can check out, and the Google Scholar profile. I'll share you the details herein. You can note down my email and the website. Now I am open to you for any queries and questions. Thank you all. Do I need to cover some more portion, or that's sufficient for all of you?
Hello, good evening, ma'am.
Yes, Simran, you can speak out any query.
Yes, ma'am. Ma'am, from my side, there is one question. Actually, I am from computer science background. So, the problem which you had discussed solving using ANN, it is little bit difficult for me to understand. Can I get some relevant stuff related to it, ma'am?
You could please write the query in the chat box. Your voice
Okay,
is cracking, it seems.
okay, ma'am. Okay.
Hello, ma'am. Am I audible to you?
Yes, yes, you're audible.
Ma'am, actually, we are doing a project on solar power forecasting. Hello. Am I audible, madam?
Kanchan, can you write in the chat box your query, please?
Okay, madam. I'll write.
About spiking neural network and how can we do research? Okay. There is no issue regarding the utilization. These days, the MATLAB particular, the software is having different toolbox directly. The app is there where you can utilize the app by presenting the patterns as an input and the target labels, and the app will be performing the task of training and giving you the final results. At the end, the app can also be finally converted into the codes, and in that codes you can change the default set parameters of the neural network and utilize it for your problem specific statement. Initially, to learn you need to check out the examples already given in MATLAB app. Any other query? Yes, for computer science background you need to understand the stuff. Main task is that you should have a set of input and target pattern, labeled pattern with you for your problem statement. They can you can usually apply the algorithm which are available in MATLAB as app. So major task in training or developing any neural network is or any machine learning algorithm is gathering the data set. If that is available with you, you can easily apply them. So any more questions from the participant side? So Sanjay sir, Sanjay Pandey sir, can you please come up and summarize?
Ma'am, thank you, ma'am. Sanjay sir is not there. Thank you very much, ma'am, for your valuable time and presentation.
Okay, thank you, Sanjay sir. I think
Oh,
your session, next session will be starting by what time, sir?
yeah. After 5 minutes, we'll start the next section,
Okay,
ma'am.
sir. So shall I leave?
Yeah, sure, ma'am.
Okay,
Sure.
thank you, sir.
Thank you very much, ma'am.
Okay, thank you, sir. Participants, if you have any query or any doubts related to application of these schemes in your field, you can mail me in my mail ID, and it is available in website also. There is no issue. I will be happy to answer to your query. Thank you all.
So, hello. We'll start the next session after 5 minutes. So, अभी कितना time हो रहा है? अभी हो रहा है 5:13 हो रहा है. 5:18 we'll start the next session. Okay, participants.
Okay, sir.
Okay, sir.
Am I audible to you? The next session will start sharp 5:35. अभी डिस्कोर्स पर्सन थोड़ा आने में टाइम लगेगा उनको सबको, तो 5:35 पे अपन स्टार्ट करेंगे नेक्स्ट सेशन.
Complete leave, once again leave.
Good evening, Anandal.
Yeah, Bala. Good evening, sir.
Yeah, okay, sir. Can I start?
Just a minute, sir. So, good evening, everyone. Welcome to the second session of day 3. So, in this session, we have Dr. Balprakash Rao, sir. So, he is working in the Department of Computer Science Engineering, NIT Warangal, as an assistant professor. He received a PhD degree from IIT Guwahati. He has more than 10 years of teaching and research experience. His research interests include software-defined networking, reliable network design, reinforcement learning, game theory, network optimization, and artificial intelligence. He published various papers in various reputed journals of IEEE, Elsevier, and Wiley publication, such as IEEE Transaction on Network and Service Management, IEEE Communication Letter, Computer Network Elsevier, Computer Communication Elsevier. He received the best paper for one of his paper in IEEE ACM CompsNet 2018. He is the reviewer of several IEEE transactions, such as IEEE ACM transaction on networking, IEEE transaction on network and service management, IEEE communication letter, computer communication Elsevier, and other journals. And he has also conducted various faculty development programs in his research area. So with this brief introduction, I request Dr. Balprakash Rao sir to start the session. Sir,
Thank you,
please.
sir. Yeah, thank you, sir. Thank you for introducing me. Okay, so let me share my screen. Share screen. I hope you can see my screen. Can you see my screen?
Yes, sir, it is visible.
Yeah,
Sir.
okay, sir. Thank you, sir. Okay.
Mm.
Okay, the topic for this session is Markov decision process. Okay, all right. So the topic for this session is Markov decision process. So this is the overview of the presentation. I'll start with what is this Markov decision process. But in order to introduce this Markov decision process, we use this step-by-step approach. So I start with this Markov process, which is one of the widely known discrete process. So we start with this Markov process, and we start with this Markov property and so on. Then we slightly change this Markov process, and we'll introduce a notion of Markov reward process. So in this Markov reward process, we will discuss various terms such as value function, Bellman equation, what is written, how written and value function are related. All these things we will introduce in Markov reward process. Then we will introduce Markov decision process. So basically this Markov decision process is a slight extension of Markov reward process. So that's why we are following this step-by-step approach. We start with Markov process, then Markov reward process, then Markov decision process. So in Markov decision process, again, we will see the value function. So the value function in Markov decision process is different from the value function in Markov reward process. We'll see the details of this value function and how it is different from Markov reward process. Then we will discuss something known as Bellman expectation equation. So this is different from the Bellman equation in Markov reward process, and we'll see how it is different. Then we will discuss the notion of optimal value and optimal policy. And finally, we'll introduce something known as Bellman optimality equation or Bellman optimal equation. So if time permits, we will also discuss how to solve these Markov decision process. If time does not permit, then we'll stop there. So this is the overview of the presentation. So we'll start with the introduction. So what is this Markov decision process? So in order to discuss this Markov decision process, it is better if we introduce the idea of reinforcement learning. So let me briefly introduce the idea of reinforcement learning here. So I hope most of you are aware of the reinforcement learning. So reinforcement learning basically comprises of two components. Two basic entities are there in reinforcement learning. The first one is agent. One is agent. The other one is environment. Agent and environment. What happened? Something happened. Okay. Let me close this. Or let me open only Paint. Paint is better. Okay. So we have two entities known as agent and environment. Agent and environment. Environment. So the agent interacts with environment. So how it interacts with environment? Agent interacts with environment by picking actions. So AI actions. So agent will pick actions. So agent interacts with environment via these actions. Then the environment will return some kind of feedback. This feedback is also known as reward. So immediately after taking an action, the environment will give some reward, right? So the environment, if you open reinforcement learning, the environment can be a fully observable environment or partially observable environment. So let us not worry about these types of environment, but how do you model this environment? So a mathematical model for environment can be captured by this Markov decision process. So basically, what is this Markov decision process? Markov decision process, it formally describes the environment in reinforcement learning. So we'll see various details of this Markov decision process, but we'll build this idea of Markov decision process step by step. So that's why we start with this Markov process. So first we start with this Markov process. So before introducing the idea of Markov process, let me introduce few other things so that it is easy to understand this Markov process. So first we'll see the idea of Markov property. So what is this Markov property? Basically, the Markov property says that future is dependent on only present. Future, that means, in other words, you can say that future is independent of past. Given present, future can be determined using the present state. There is no need of the past information or the past states. So this is called Markov property. So mathematically, this can be represented like this. So we say that, so those who know the idea of reinforcement learning or this Markov process, they know that there are something called states. We'll see what is the state and all. So basically, we say that a state is Markov. Suppose ST. So here ST represents the state of the agent. Let me write here. So what is ST? ST is the state of the agent at time t. So the subscript indicates that it is time. So t is time. At time t, ST is the state of the agent at time t. Now, at time t plus 1, what is the state of the agent? We want to find out what is ST plus 1. Right. At time t plus 1, what is the state? At time t plus 1, the state may be, let us say this is ST. It may be either S or it may be S dash. So basically, the Markov property says that if the present state is ST, then what is the state at ST time t plus 1? So the probability that the agent will be at state ST plus 1, this can be determined using the present state. So this is equivalent to what is the probability that this agent will be at state st plus 1 given the past information. Past information means what? S1 to st. If you know the past information, this past information does not add anything. If you know the present state, then the past information doesn't add anything. That's all. This basically says that. So the probability that the state of the agent at time t plus 1 given the present state is same as probability that the agent will be at st at time t plus 1 given entire information s1 to st. So that means what? Here we call this s1 to st as a history. So s1 to st is the history. St is the present state. St plus 1 is the future state, right? The next state. So basically, if the present state is known, then this history is of no use. So therefore, if the history is of no use, then the history can be simply thrown away. That is the idea of this Markov property. So we will use Markov process, Markov reward process, Markov decision process. All are based on this idea of Markov property. That's why the name Markov comes in everywhere. Markov process, Markov reward process, Markov decision process. So that means if you know the current state, then you can determine the next state based on the current state. Okay. Then we'll see some notations. These notations will be used again and again. So suppose you are at state S and the next state is S dash. So what is the probability that your next state will be S dash? It can be represented using this PSS. So PSS dash basically says that this is the probability. So what is the probability that the agent will be in state S dash at time t plus 1 given that the current state is S. Current state is S, then the next state is S dash. What is that probability? That probability is represented using PSS dash. Then we'll slightly change this transition. So this is a single transition probability. Then we introduce something known as state transition matrix. So this state transition matrix is denoted with this capital P. So here each entry in the transition probability matrix basically represents. So if you have, let us say, if you have n states, 1, 2, 3, and so on. Suppose you have ith row and jth column. Ith row, jth column. So the ith row and jth column, the entry corresponding to this ith row and jth column is Pij. So basically Pij represents that what is the probability that from state I, it will go to state J. So that's why it is called transition. Transition means what? I hope many of you have an idea about these formal language and automata theory or theory of computation course. There you will have the state transition probabilities, right? S1 and S2. If these are two states, S1 to S2, this is called transition, right? From S1 to S2. So here we call it as transition probability. So that means if you are in state S1, what is the probability that you will move to state S2? This can be represented as P12. So all the state transition probabilities can be captured using this state transition matrix. Okay. Now we will introduce the idea of Markov process. So basically Markov process can be represented using two things. One is set of states, the other one is transition probability matrix. So this Markov process can be represented using this set of states and this state transition probability matrix. So what is this Markov process? Markov process is basically a random process with Markov property. You can explore the idea of random process because this is an extension of your random variable, right? Random variables over the time we call random process. So basically Markov process is a random process with the Markov property that we discussed just now. So a Markov process is set of states followed by a state transition probability matrix. Now let us see an example of this Markov process. Here, if you see, we have an example of Markov process. What is this example? Here we have a student. We have a student, and here the states represents. Here you see class 1, class 2, class 3, pass, sleep, Facebook, pub. What are these? These are the states, right? And then, so what are the states? So here the states, so capital S is states. States are class 1, class 2, class 3, sleep, Facebook, pass, sleep, Facebook, pass, and pub. Right. Now, if you see the transition probabilities, C1 to C2, we have some value here. What is this value? This is the probability. So that means after attending class 1, with 0.5 probability, he will go and attend class 2. With other 0.5 probability, he will not listen to class 2. He will go outside and he will open some Facebook and he will do something. After attending class 2, with 0.8 probability, he will attend class 3. After attending class 3, with 0.6 probability, he will write the exam and he will pass. After passing the exam, then he will go and sleep. That means he will have a break, right? We will have these semester breaks. So this is kind of semester break. After passing, after writing all the exams, then you can take rest for some time. So this was like that. So here we have a Markov process of student, right? Markov chain of student. So here, if you see, if the student, let us say, starts in class 1, right? Then we have different state transitions. From class 1, he may go to class 2, then class 2 to class 3, class 3 to pass, then sleep, right? Now, if you see, here we have a different kind of state called sleep. So if you see the sleep state, there are no transitions that are going out of this sleep state, right? So this state is called terminal state. So terminal state means, terminal state is a state from which there are no outgoing transitions, right? So from the sleep state, we are not going outside. Whereas from all other states, we have outgoing transitions. So if you take episode means an instance of this student moment, then you can see this is an episode. After attending class 1, he will attend class 2, then he will attend class 3, then he will write all the exams and he will pass the exams. Then he can take a break, semester break. The other one, after attending class 1, then he will take a break. Means he went and he checked Facebook, then Facebook. Then again he came back to class 1 because he left it in between. Again he attended class 1, he attended class 2, then from after class 2 he slept. So these are different episodes. Now if you see this Markov chain, what is the probability transition matrix for this Markov chain? So this is the probability transition matrix for this Markov chain. So if you see, all the rows and columns are states, right? So if you see C3 and pub, so that means after attending class 3, what is the probability that he will attend pub? He will go to pub. It is 0.6. So with 0.6 probability, after class 3, he will go to pub, right? So for any questions, this Markov process?
Sir, how to decide which will be our initial state?
Which will be?
Our starting or initial state?
Means for this example or
Generally, if we want to apply this to some problem, so how to decide that this will be our starting state? Like we have taken class one, so we would have taken class two first.
Okay. So everywhere you will have some initial configuration, right? So that initial configuration will be taken as initial state. State means what? It will capture some information about all the variables, information about parameters, and so on, right?
Okay.
Yeah, so that initialization will be taken as the starting state. That's where you start. Okay, all right. Then, okay, any other questions? Okay, then we'll move on to this Markov reward process. Okay, now if you see the name itself, the only change is reward. Earlier we have Markov process, now we have Markov reward process. So therefore, it is easy to understand this Markov reward process. So Markov reward process is an extension of Markov process. So basically Markov reward process is a Markov process with an additional component called rewards. So that's why this Markov reward process can be represented using these it is represented using these four components. One is set of states that we already know, and the second one is transition matrix, right? Probability transition matrix. So this is represented using P. Then the third component is R. So this R is basically reward function. R is basically reward function. Then we have one more component called gamma. Gamma is called discount factor. So the value of gamma is between 0 and 1. It can be any value between 0 and 1, including 0 and including 1. So now first we'll see the reward. What is this reward? So while discussing this idea of reinforcement learning, we said that agent will take an action, then the environment will give some feedback, right? This feedback is also known as reward, right? So basically reward means what? This basically the reward captures okay, this is different. That reward that reward I will introduce, but for now let us assume that reward means feedback. That means if the reward is some positive value, then the feedback is good. The feedback from the environment is good. If reward is a negative value, then it can be assumed that the feedback is not good. So basically the reward function here, if you see again, we'll change this reward, but for now reward is associated with state. That means what? If you are in state S, then you will get some reward. If you are in state S, you will get some reward. That means what? Suppose you are in state S1. Before moving to S2, you will get some reward, which is called R of S1. Similarly, when you move to S2, you will get a reward S2. From S2, if you move to some other state, let us say S dash, then the reward is RS dash. So here in Markov reward process, we associate reward with state. That's why if you see the reward function, what is reward? Reward is if you are at state S, what is the reward that you will get at time t plus 1? That means what? At time t, you are at state S1 at time t. At time t plus 1, you have moved out of this state S1. So before moving from state S1, you will get a reward corresponding to this state S1, which we call as RT plus 1. You can use a different notation. Rather than writing RT plus 1, you can write RT also. It is up to you how do you represent. But here we are using the notion of RT plus 1. So what is RT plus 1? RT plus 1 is the reward of state at time t. Then the last component is called discount factor. Discount factor is a value between 0 and 1. So we'll see the idea of discount factor. But before that, let us see a Markov reward process example. So the same student Markov process or Markov chain was extended to this Markov reward process. Now what is the change? The only change is highlighted with this red text. So you see, for every state we have written some reward. So for class 1, what is the reward? -2. For class 2, what is the reward? -2. For class 3, what is the reward? -2. So if you see, now you may ask, what this -2, -1, 0, +1, +10 basically represents? That means if you see -2, so feedback is not good. Not good means basically what? While you're attending a class, you have to focus on the class. You have to what? Use your brain, right? Which will suck your energy, right? So that's why here -2. That means you have to spend some energy while attending the class because you have to be focused and so on. Now, if you see pub, so that means you went to pub to enjoy. So your mind is free, everything is free. So the feedback is +1. So let us say the environment is your mind. Your mind is giving this feedback. So while attending class, your mind will resist you to attend the class. So that's why the feedback is -2. But when you go to pub, your mind will not resist, right? You will enjoy. So that's why it is +1. But that enjoyment is what? Short-term enjoyment. That's why the value is +1. But here, if you see, when you attend all the classes, let us say, rather than classes, you can say semesters. Let us say 3 years. This is first year, this is second year, this is third year. Let us say you have a 3-year course, 3-year program, some program, a degree course or something. So after finishing all these 3-year courses, you write the exams, you pass. When you pass all these exams and you get a certificate, you will get a what? Feeling that okay, now I got this certificate. So you will be happy, right? That's why the value here is 10. So that's why we assigned rewards to states. Okay, so before going to Markov decision process, we'll introduce few ideas. These ideas will be extended to Markov decision process also. So first idea that we'll introduce here is what is written. So basically written is represented with this notation GT. Written is represented with the notation GT. So what is GT? If you see, GT means what? From time t onwards, what is the reward that you will get? At time t, what is the reward that you got? How we represented that reward? The reward that you get at time t, we represented with RT plus 1. Then what is this GT? This is written. RT plus 1. We used RT plus 1 rather than RT, right? Don't confuse this. So this is the reward at time t. We represent with RT plus 1. There is a small abuse in the notation. So we'll see what is written. Written means what? From time t onwards, how much reward you got? What is the cumulative reward? What is the cumulative reward that you get from time t onwards? So this is called written. So basically, at time t, what is the reward? RT plus 1. At time t plus 2, what is the reward? RT plus 2. At time t plus 3, what is the reward? T plus 2, what is the reward? RT plus 3. At time t plus 3, what is the reward? RT plus 4, and so on. So if you add all these rewards,
So this +1 at t is due to that the reward will be given after the transition.
yeah, it is not after the transition. Before moving out of the transition, okay, let us say after the transition. So this is the reward for being at state. So basically, you can avoid this notation also. You can use RT plus 1 also, but in this presentation, it was in a different way. You can avoid that. So RT means what? At time t, you are at some state. And what is the reward from that state? What is RT plus 1? At time t plus 1, you are at some state. And what is the reward from that state? So, right? That's why the reward was defined with respect to state. So what is RS? RS is basically at RT. Suppose at time t, if your state is yes, time t, your state is yes, then what is the reward that you will get from this state S? We call RT. Is it okay? So at time t, your state is yes, then the reward is RT. So then what is GT? GT is RT plus RT plus 1 plus RT plus 2 plus R3 plus 3 and so on. That means the cumulative reward that you will get from time t onwards. Time t onwards. We call it as return. So I will explain this with an example also. Don't worry. Now we have one more thing here. What is this? Gamma. So rather than RT plus 1 plus RT plus 2 plus RT plus 3, we have one more parameter, gamma. This is gamma square, gamma cube, and so on. So what is this gamma? What is the significance of this gamma? And why this? So what actually this return means? We'll see with an example now. So basically, suppose you are earning some 40k or 400k per year. Okay, so let me take few assumptions here so that it will be easy to easy to understand what we are discussing. Let us assume that your salary will not change. It will remain same. Every year it will be 400k per year only. And then your lifetime is 60 years. Or okay, let's be optimistic, 80 years. Let us say lifetime is 80 years. Right? And we know this. Let us assume that we know this. Now your current age is 40. Your current age is 40. So what is your return? Every year you will get this 400k. So what is return? Return is basically 400k this year, then 400k next year, 400k next year, and so on until 40 to 80 years. Is it okay? So this is called return. This is the cumulative reward that you will get. So let us say the reward is the salary. The salary that you are getting is 400k per year. Is it okay? So what is the return? Total return is 400k, 400 plus, and so on. This is called return. What is reward here? Reward is 400k. Whereas return is 400 plus, 400 plus, 400 plus. That means it is 400 into 40, let us say. 16,000k. But we have this discount factor. Return is not straightforward. We have this discount factor. So what is this discount factor? Basically, let me give another example to understand what is this discount factor. So this discount factor means what? So you have 1 lakh rupees at your hand. You have 1 lakh rupees at your hand. Right. Otherwise, let us say 20 lakh rupees. 20 lakh rupees at your hand. Right. This is 2023. Now, for this 20 lakhs, let us assume that you can buy a house. Right now, you can buy a house for 20 lakhs. You can buy an apartment or whatever it may be. Let us assume this. You can buy a house for 20 lakhs in 2023. Now, suppose you postpone this decision of buying a house. You postpone till 2024. Right? Now, do you think you can buy a house for 20 lakhs, the same house in 2024? Same kind of house, let us say. Let us say you want to buy an apartment for 20 lakhs in 2023. So for 2024, the cost of the apartment may increase. This is due to inflation and various other factors. I hope you can understand this, right? So in 2024, if you go to market to buy an apartment, you may not get an apartment at 20 lakhs. The builders may ask you for more money. They may ask you 24 lakh. They say that no, cost of raw material was increased, cost of land was increased, cost of labor was increased, everything was increased. So it is not possible to sell a house at 20 lakhs. So the current price of the house is 24 lakhs, right? So this is due to the inflation, right? So this is the idea of this discount factor. That means what? When you have 20 lakhs, so that means it is the other way. When you have 24 lakhs in 2024, then it will be equivalent to what? So let us round off. Let us round off 10 lakhs. Let us say 10 lakhs. This is 12 lakhs. 10 lakhs or 11 lakhs. This is 11 lakhs. That means what? The cost of 11 lakh in 2024 is equivalent to 10 lakh in 2023. Is it clear? So 10 lakh in 2023 will be equal to what? $10 lakh in 2023 will be equal to what in 2024? It is
14 lakhs.
not 14 lakhs. This is 11 lakhs, let us say. No, the price of the house is 11 lakh in 24. Price of the house is 10 lakh in 2023. So what is the value of 10 lakh in 2024? It is 10 by 11 into 10.
10% extra.
10% extra, 10% below. Right? Now it will be around 9 lakhs, 9 lakhs, 10,000 or something. Do you agree? So the value of 10 lakhs in 2024 is only 9 lakhs 10,000. So this is called the discount factor. Is it clear? So if you have 11 lakhs and the value of 11 lakhs in 2024 is only 10 lakhs. So this is called the discount factor, 0.1% discount factor. So that means the value of your money was reduced by this 0.1%. So this is called the discount factor, gamma. So gamma captures this idea, the idea of depreciation. Okay, so that's why if you see here, what is this reward? This is the reward. So that means let me put it other way. So suppose you are getting 400 K per year, right? 400 K next year also. It will not change. That's what we assumed. Now, right now you are sitting and you are calculating how much I will get. Right? You are simply adding this 400K doesn't give you the actual value. Right? So after 40 years, let us say you got 16,000K. 16,000K. Now, after 40 years, the value of 16,000K may be very less, right? It may be equal to, let us say 5,000K at the current price, right? Because after 40 years, do you think it is same? 20 years back, the salary was only 10K. Now the salaries was increased, but everything got increased, right? So this increase in number has no value. So the 16,000K after 40 years has no value. But you are calculating right now. So since you are calculating right now, you will not get the 16,000K right now, right? You will get this value after 40 years. So that's why you have to introduce this discount factor into the equation. That's why it is RT plus gamma times RT plus 1 plus gamma square times RT plus 2 and so on. That means every year it depreciates. Gamma cube into RT plus 3 and so on. So this is the idea of this discount factor. Is it clear? Any questions?
The reward will not be getting increased with the years.
Reward. Okay, here the assumption that I have taken is reward is same. For understanding, I took this. It may change
Okay.
also. It may vary also.
Okay.
This generally the reward at different states is different. This is 500. This may be 450. Right? It is dynamic. Right? It is 550 maybe. But whatever may be the value, we multiply with gamma. Is it clear? So 500 next year may be equivalent to 400 right now. Right? The value of 500 rupees next year is equivalent to only 400 this year. Is it clear? If you want even a simple example, I give this gold example. Otherwise, suppose you have 1 lakh rupees. 1 lakh
Sir,
rupees.
can we take an example with some data set, real time data set, so that it will be easy?
But data set explanation is not that easy. This since it is fully mathematical, explaining those mathematical with again data set. Okay, let me give this example, then at least you will understand. Let us say you have 1 lakh rupees. Let us assume that with this 1 lakh rupees, you can buy 10 grams of gold right now in 2022, 2023. So if you go to 2024 with 1 lakh rupees to buy the gold, you may not get the same 10 grams, right? Because the value, the cost of the gold is increasing every year, right? So let us say in 2024, if you get only 5 grams gold for 1 lakh. Now, what do you say? What is the discount factor? What is the discount factor? The discount factor gamma is 0.5 because it got reduced by 50%. Right? 1 lakh rupees has only half the value next year. That is the idea of discount factor. Okay, there are many reasons why we introduce this discount factor into this Markov decision process. I will share the slides. You can go through the reasons because we have to go to Markov decision process. Okay, so far what we have discussed, we only discussed this return. What is return? Return is cumulative reward from time t onwards. Now we introduce one more notion called value function. So basically the value of a state is called long-term reward or long-term value of state S. So that's why we introduce this idea of return. This value function can be understood if you know the return. So what is value? If you see the mathematical definition of value of a state, value of a state is nothing but, suppose at time t, you are in state S. From that state S, so at time t, you are in state S. So what is the total return from time t onwards? So what is the expected return from time t onwards? This is called value. What is value of a state? Value of a state is nothing but the expected return from time t onwards, given that at time t you are at state S. So this is called value of state S. So now one may ask, why there is this expectation? Why this expectation is there? It will be clear when we move forward, these expectations and everything. Why expectation was there, all these things. So therefore, we have already discussed what is this return. So now let us go and calculate this return. Suppose if this is the episode C1, C2, C3, pass, sleep. If this is the sequence of transitions from C1 to C2, C2 to C3, C3 to pass, pass to sleep. Now what is the total cumulative reward that he will get from state C1 onwards? What is the cumulative reward that he will get from state C1 onwards? So for that you can go and check this figure. So we are at C1. So what is the episode we have written? The episode that we got is C1, C2, C3, pass, sleep. Now how to get the return from C1? That means what? How to get G1? How do you get G1? What is the reward from state C1? What is the reward from state C1? -2, isn't it? So it is -2, right? Let us assume that the gamma is 1. Here what we assumed, gamma is half. Let us assume that the discount factor is half, right? So after -2, what do you get? Gamma times reward from next state plus gamma square times reward from next to next state plus gamma cube times reward from next to next state, and so on till the sleep. So how do you get? This is -2 plus what is gamma? Half. What is the reward from state C2? What is the reward for state C2? It is -2 plus half square times what is the reward from state C3? What is the reward from state C3? -2 plus half cube from what is the reward from pass? What is the reward from pass? 10 plus half times 4 times what is the reward from sleep? What is the reward from sleep? 0. So what do you get? -2 -1 plus 1/4 times -2 plus 1/8 times 10. So what do you get? You see what do you get? You get this one. How much we get? -2.25. Similarly, you can get the reward from state C1 for different kinds of episodes. Is it clear? So this is an example how we calculate reward.
So, sir, in what situation these returns will be less, and in what situation the returns will be more?
Okay, that we'll discuss, but since you asked, I will tell. So in what situation the returns will be more, and what situation the return will be less. That's what you are asking, right? So suppose you are at state S1, right? You have state S2 here, you have state S3 here. Now from S1 to S2, you can move from S1 to S2, or you can move from S1 to S3. So if the value of the state S2 is 100, if the value of the state S3 is 50, then the return from S1 will be more if you move to S2 when compared to S3. That means from S1, if you move to S2, then the return will be higher when compared to S1 to S3. Is it clear?
Okay, but if it is like S1, S2, and then S3 and S4, and
Okay,
S3 is having less.
Yeah, S3 is having less and S4 is having?
Yes, more.
More, right. So that's what we take the cumulative. So from S1 to S2, how much we got? Let us say S1 is fixed 10. S1 is 10. From S2 100. Let us say S4 is less, means how much? Can you tell?
It's like 40.
40.
60.
Okay, 60. Now tell me, 10 plus 100 plus 60, how much? 170.
170, yeah.
10 plus 100 plus 50, how much? 160. So which one is better? So it is better to go from S1 to S2 than S2 to S4. So this will slightly build it. We'll build with mathematics actually. Don't worry, we'll build it slowly. I understood your question, but we'll build it slowly. Yeah. So this is how we calculate return. Now, here we are calculating value of a state. So what is value of a state? How we define value of a state? Value of a state is expected return from state at time t. Right. So here, what is the state at time t? S. That's why it is called value of state S. Now tell me how to calculate value of this. Let us say some example. -2. How do you calculate? When gamma is 0, what happens? What happens when gamma is 0? When gamma is 0, what happens to GT? Can you tell? GT is simply RT plus 1, right? So that means this is the reward from state at time t, isn't it? So that's why here if you see value of this state is nothing but the immediate reward -2. Value of this state is -2. Value of this state is -2. Value of this state is 10. Value of this state is -1. Value of this state is 0. Value of this state is +1 because gamma is 0. Now we'll see when gamma is 0.9. When gamma is 0.9, how do you calculate? So this we have not yet introduced, but we'll slightly come to this. So these are the values of each and every state when gamma is 0.9. Similarly, these are the values of each and every state when gamma is 1. Okay. Now to answer your question, right? You are asking, right? So now we'll define the value recursively. Then we'll understand this. So we'll extend this. What is value? What is value? Value is, what is value of a state? Value of a state is nothing but expected if the at time t, if this agent is at state S, then what is the return from state S? Right. That's what we define. What is value of state S? If time t, if you are in state S, then what is the return from time t, gt? But we have a equation for gt. What is gt? What is gt? It is RT plus 1 plus gamma times RT plus 2 plus gamma squared times RT plus 3 and so on, given that the current state is S. Now you can do some algebra. What is the algebra that you can do? You can take gamma common here, right? If you take gamma common, it becomes RT plus 2 plus gamma times RT plus 3 plus gamma squared times RT plus 4 and so on. It will continue, given that ST equals to S. There is no need to write this. Now, if you observe closely, this is RT plus 1 plus gamma times, what is this? What is this?
GT plus 1.
Yeah, this is GT. This is GT plus 1, right? This is GT plus 1. But here again, we take the expectation, right? This is GT plus 1 basically, GT plus 1, given that ST equals to S. So, right, GT plus 1. Now, if you apply the expectation everywhere, so what happens since it is expectation? So this becomes expectation of RT plus 1 plus gamma times the expected value of GT plus 1 will be V of the successor state S dash. You see here, that's what S dash or ST plus 1, whatever you write, ST plus 1. So if you apply the expectation here, this becomes the value of state at time t plus 1. Is it clear? So this is the recursive definition. So a value of a state has two components. What are the, so from this last equation, it is clear that value of a state has two components. What are the two components? One is immediate reward. The other one is value of the next state. Is it clear? Immediate reward plus discount factor times value of next state. So this can be visualized like this. What is value of status? Value of status is the immediate reward plus the discount factor times value of the next state. But what is the next state? Yes, maybe like just now you have asked, right? Just now someone has asked if state S has two successors from S, you can go to S1 or you can go to S2, right? So what is the probability that from state S you will go to S1? This is represented with PSS1, right? What is the probability that from state S you will go to S2? It is represented with SS2, right? So now what is the value of state S1? Let us represent with V of S1. What is the value of state S2? Let us write it as V of S2. Now what is value of S? Can you tell what is value of S? So you are at state S. So since you are at state S, you will get a reward. What is that reward? RT or RT plus 1. RS. Let us call it as RS. This is called immediate reward. So this immediate reward, this reward is for being in state S plus the discount factor times value of next state. What is the next state? Is it S1 or S2? That next state depends on this probability transition, right? So P of SS1 times value of S1 plus P of SS2 times value of S2, right? So this is the value of next state because it is not sure where you will be. Let us say this is 0.5 probability will be in S1 with 0.5 probability will be in S2. So we multiply 0.5 with value of next state S1. Similarly, 0.5 times value of S2. Is it clear? So therefore, we change the value function like this. What is value of a state? It is immediate reward plus discount factor times the possible successor state. So S dash is the successor state. S is a set of successor states. For every successor state, you multiply the transition probability and value of the next state or successor state. Is it clear, this one?
Yes, sir.
Okay. So now this is called Bellman equation. This particular equation that we have derived just now is called Bellman equation for Markov reward process. So if you apply the Bellman equation for this student Markov reward process, and if you see how do you calculate value of this particular node 4.3, if you go back and see, you want to calculate value of this. Okay, yeah, for this we got 4.3, right? How we got this 4.3? How we got this 4.3? Because what is the immediate reward? Can someone tell me what is the reward for this state? Reward for this state, C3. If you are in C3, what is the reward you will get? -2, right? That's what written here. That's what we discussed. So -2 is the reward that you will get when you enter into C3. Okay, so what is the value of this state? Value of this state is the immediate reward plus discount factor. Discount factor has no use because it is 1, right? Times 0.6 probability, it will go to this state. What is the value of this state? 10. And 0.4 probability, it will go to this state. What is the value of this state? It is 0.8. So that's why if you see here, how you got this 4.3? 4.3 is -2 plus 0.6 into 10 plus 0.4 into 8. That's how we got 4.3. Is it clear? Is it clear how we got? That's why we have postponed this discussion. How the values, how we got these values. Any questions so far?
Okay, sir, it is clear.
Okay, if no questions, then we'll move on to the Markov decision process with this few how to solve Markov reward process. We'll see, then we'll move on to Markov decision process. So if you see, what is value of state S1? What is value of state S1 or V of 1? How to write V of 1? Suppose you have n states. You have n states. 1, 2, 3, 1, 2, 3, and so on, n. How do you find out value of state S1? It is nothing but, what is the immediate reward from state S1? It is R1, right? Plus R1 plus some discount factor is there, gamma times. From 1, you may go to again 1, or you may go to 2, you may go to 3, you may go to 4, and so on, you may go to n. So what is value of 1? It is R1 plus gamma, you leave it. Then what? Then P11 times V1, P12 times V2, P13 times V3, and so on. Do you agree? P1n times Vn. Right. Similarly, what is V2? How do you find out value of state 2? It is nothing but R2 plus gamma times P21 times V1, P22 times V2, and so on, P2n times Vn. Similarly, you can calculate Vn. Right. So if you combine all these equations, we can write it as a matrix. How to write it as a matrix? You can take all left-hand side into a vector. All left-hand side into a vector. So what it will give? It will give something like this: V1, V2, and so on, Vn equals to what? Equals to what is the first component here? R1, R2, and so on, Rn. Here it will be Rn plus something, right? So you will have a vector here again. What is this vector? R1, R2, and so on, Rn plus gamma is common. Gamma times. You see here, this is P11, P12, P13, P1n, right? So you will have a row for all these things, P1n. Similarly, Pn1, Pn2, so on, Pnn, right? So P11 times what? V1. So you see here, values are same everywhere, V1 to Vn. Only thing that is changing is these P probabilities, right? That's why we can write it as a matrix like this. Do you agree? You can calculate value of each and every state. So you can represent value of each and every state in this matrix vector notation. Do you agree? V is a vector, R is a vector, gamma is a constant, P is a matrix, V is a vector. Right? Right? Now, how do you calculate V? What we want to find out? We want to find out value of each and every state. How do you find out value of each and every state? What we have so far? We have so far a matrix representation. V equals to R plus gamma times P times V. P is a matrix, V is a vector, R is a vector, V is a vector. Now, how to find V? In order to find V, take this side, V minus gamma times PV equals to R. Right? If you take V common, V equals to 1 minus gamma times P equals to R. 1 minus gamma times. 1 minus means what? This is like all ones. Or some this is also a matrix here. 1 means, right? So now how do you find out V? V is nothing but, since this is a matrix, this is a constant, this will be a matrix. So therefore this is a matrix. So when you take this side, it will become 1 minus gamma times P inverse R. So you can find out value of each and every state in Markov-Reward process by simply calculating the inverse and multiplying with the rewards. Is it okay? So if you find out inverse, then you can calculate value of each and every state. But the problem here is, if the matrix size is very large, then the computation of inverse will take it will take order of n cube time. So it will be very large, right? To reduce this time complexity, we can go for dynamic programming and other methods, Monte Carlo evaluation, temporal difference learning, and so on. Now we'll introduce this Markov decision process. So now we have discussed some of the things in Markov-Reward process already. Now we'll see the other things in Markov decision process. So now the Markov decision process is an extension of Markov-Reward process. So basically, Markov decision process is a Markov-Reward process plus an additional thing. That additional thing is called decision or actions. So basically, MDP is MRP plus actions. That's why if you see Markov-Reward process, we have states, we have state transition probability matrix, we have rewards, we have discount factor. What is extra? The only thing that is extra here is action. Okay, is it clear? Only thing that is extra here is action. So therefore, now we try to change everything. Earlier, the transition is from state to state, right? So we represent with P, S1, S2, right? Transition is between states. But now the transition is upon action. That means at time t, if you are at state S, and at time t your action is A, then your state at time t plus 1 will be S dash. So this we represent it as P of S dash with an action A. That means what? You are in state S and your action is A, and what is the probability that your next state will be S dash. So now the state transition probability is with respect to action. Similarly, the reward, if you see the reward is also with respect to actions. It is no longer with respect to state. So earlier the reward is with respect to state. Right now it is no longer with respect to state. It is with respect to action. That means what? You are at state S and your action is A. Then how much reward you get? The reward that you get upon action A from state S, we represent it as RS superscript A. Is it clear, this notation? So the transition and reward are with respect to action. They are not with respect to state alone. Earlier the transition is with respect to state alone. Reward is with respect to state alone. But now it is with respect to state and action. Is it clear, first of all, the difference?
Yes, sir.
Okay, now we'll extend that MRP to MDP. Now if you see the reward, earlier if you see the figure, where is that figure? Yeah, this figure. The rewards were associated with state, but now the rewards are no longer associated with state. You see, reward is associated with action. Action means what? You see, if you study, then you will get reward -2. If you study, you will get a reward -2. If you study, you will get a reward 10. If you quit, you will get a reward 0. If you open Facebook, you will get a reward of -1, and so on. Is it clear? Okay. Okay, then now we introduce one more thing. It is called policy. Basically, policy defines the behavior of the agent. So that means what? There are two kinds of policies: stochastic policy and deterministic policy. But let us not worry about deterministic policy. Let us discuss this stochastic policy. Deterministic policy is a specific case of stochastic policy. So basically, what is this stochastic policy? Basically, policy means it gives the distribution of actions, given state. That means what? Suppose we are at state S. Let us say the possible actions are A1, A2, A3. Basically, the policy says that, okay, you are at state S. What is the probability that you will pick action A1? What is the probability that you will pick action A2? What is the probability that you can pick action A3? So basically, policy is represented with this phi. Since it is a deterministic policy, you are at state S. What is the probability that you will pick action A1 from state S? Let us say this is 0.4. Pi of A2S is, let us say, 0.5. Pi of A3S is like 0.1. That means what? If you are in state S, the probability that you will pick action A1 is 0.4, probability that you will pick action A2 is 0.5, probability that you will pick action A3 is 0.1. So this is called policy. So basically, policy will tell you what action you will take in a state and what is the probability with which you will take that action. This is not required. Now we'll define these important things: value function and Q value function, state value function, and action value function. Then we'll introduce Bellman expectation equation, and then Bellman optimal equation also. So what is value of state? Now you see the only difference here is with respect to policy. Why this policy was introduced here? Earlier there is no policy. If you see what is value, what is value here? This is simply value of status, that's all. But here it is not value of status. This is value of status with respect to policy phi. What is the use of this policy? The policy will tell you what action to take and what is the probability with which you take that action, right? So basically policy will tell you what action you will take in a state. So basically now the state value function, if you see, that means this is the value of a state following policy phi. Value of a state following policy phi. Now how do you compute this value of state as following policy phi? So this is again expected return following policy phi. The expected return. So everything is same. Only thing is you are following policy phi. Now, what is action value function? So the action value function is basically the expected return following policy phi, but in status your action is fixed. In status your action is A. From next state onwards your action is based on policy phi. Is it clear the difference between action value function and state value function? Any questions here? Let me give this example, at least then you will understand. Suppose you are at state S1. You are at state S1. You have S2, S3, S4, S5, S6, then S7. So basically the policy means what? Policy has to tell you what is the action corresponding to each state. Now for simplicity, let us assume that it is deterministic policy. Deterministic policy means what? What is the action at state S1? Action at state S1 is let us call it as 1, 2, 3. Let us call it as 3, 2, 4. Let us call it as 6, 5. Right? What is the action at state S1? It is 2. Let us say this is a policy. What is the action at state S2? 5. What is the action at state S5? 7. What is the action at state S6? 7. What is the action at S3? 6. What is the action at S4? Let us say 5. 5. From here it will go to here, then it will go. Now this is your policy. So what is value of state S1? How do you calculate value of state S1? Following policy phi. So from S1 you simply blindly follow the policy. From S1 you go to S2 because phi of S1 is 2. From S2 where will you go? You go to 5. From S5 where will you go? 7. That's all. Right. So for every action, now here from S1 you went to 2, so you will have a reward. What is the reward corresponding to this? Action is 2, state is S1. From S2 you went to S5. What is the reward? It is S5 from state 2, S2. From S5 you went to S7. So this is R of S5. What is the action? 7. Let us call it as 7 only. Right. So from S1 you go to S2, from S2 you go to S5, S5 you go to S7. So then you calculate the reward. This is this plus gamma times this plus gamma square times this and so on. This way you calculate. That is called value of a state S1 because you are following policy. Now we define something called Q value. So the Q value is defined with respect to not just state, with respect to action. So what are the possible actions from state S1? It can be 2. It can be 2, or it can be 3, or it can be 4. That means what? Let us take this one. Or let us take this one. Then you will understand. So that means from state S1, your action is fixed. From state S1, what is your action? Go to S3. But from S3 onwards, that means what? From S1, you went to S3. From S3, where will you go? From S3, where will you go? Let us say from S3, again, there are 2 possible actions, 6 and 5. Now, where will you go? From S3 onwards, you follow the policy. For S1, you will not follow because from S1, the action is fixed. The action corresponding to S1 is given 3. From S3, from next state onwards, you follow the policy. From S3, what is the action? 6. You go to 6. Then 6, what is the 5 of S6? It is 7. You go to S7. Is it okay? So what is the reward you will get here? Reward you will get here. Reward you will get here. You calculate all this. So this is called Q value. Similarly, you can calculate Q phi of S1, 4. So you fix the action in the initial state, the state. SA means you fix the action corresponding to the state. From next state onwards, you use the policy. So these are the Q values for this Markov decision process with gamma equals to 1, and this is a stochastic policy. Stochastic policy means what? You see, at any time there are only 2 outgoing edges at any state, right? This is one state, this is one arrow, this is other arrow. From here you can see one arrow, other arrow, and so on, right? By the way, this is not a state. The state was represented with this circle. That is the only change here. So only there are 2 successor states, right? So phi of A given S equals to 0.5 means the probability that it will go to next state, either this state or this state, is 0.5. So these are the values of each and every state. How it was calculated, we will see shortly. So now we'll introduce this Bellman expectation equation. Then we will find out how we got these values. How we got these values. Now, this Bellman expectation equation, before going to Bellman expectation equation, we have Bellman equation, right? What is that? V of S equals to expected value of RT plus 1 times gamma times V of ST. Where is that? We already got in MRP. This is what we got. You see, V of S equals to E of RT plus 1 times gamma times V of ST plus 1, given that ST equals to S. So now the only change is policy. You see here. So then it is called Bellman expectation equation. Value of a status following the policy phi is the expected value following the policy phi. Similarly, the Q value can be defined in a similar way. But we will analyze this. Now we will try to analyze this. Then we will understand this. So let us say, let me write this way. Here when we write, then at least you will understand. You are at state S. You are at state S. You are at state S. And you want to find out, let us say we have a policy. Policy is fixed policy phi. Now we want to calculate V phi of S. How do we calculate V phi of S? That is the question here, right? From state S, you can have multiple actions, right? You can have multiple actions. So the probability of taking this action was represented with phi of A given S, right? Let us say this is action A1, this is action A2. So this is phi of A2 given S, this is phi of A1 given S. So this is the probability was represented with this phi of A1 given S, phi of A2 given S, right? Is it clear? So let us say if your action is A1, then you may go to some state. If your action is A2, you may go to some other state. Then how do you calculate V phi of S? So V phi of S is nothing but, for taking an action A1, you will get an immediate reward. What is that reward? That is R of A1 given S. What is the immediate reward that you will get here? This is R of A2 given S. Now, how do you calculate value of status? Value of status is nothing but R of A1S plus R of A1S plus, let us say this is S1, this is S2. Gamma times value of S1. Gamma times value of S1. Gamma times value of S1. And what about this one? Here we get R of A2S plus gamma times V of S2. Right. So this is the reward that you get here. This is the reward that you get here. But if you see here, we have some probability here. What is the probability with which you take this action? What is the probability with which you take this action? Right. So that means you have to multiply with this. You have to multiply with this phi of AS. So here you have to multiply with phi of A1 given S, and here you have to multiply with phi of A2 given S. So this you have to multiply with this you have to multiply with this, then you have to add this, then only you will get V phi of S. So therefore, how we can write this one? If you see this one, now if you see clearly, what is this? What is this? This is nothing but Q of phi given S comma A1. This is nothing but what? Q phi given S comma A2. Why? Because here at status you fixed action A1. Here at status you fixed action A2. Then this is the reward that you got. This is the reward, long-term reward that you got after fixing the action at status as A2. This is the reward that you get after fixing the reward at status as action at status as A1. Right. So this is phi, Q phi of SA1. This is Q phi of SA2. So therefore, V phi of S is nothing but phi of A given S multiplied by Q phi of S given A. We take this over all actions A. Is it clear how we got this equation? Because our further discussion will be based on this. Any questions here? How we got this? Note that this is not transition probability. This is the probability with which we take the action. Okay. Any questions? Please post in chat box. So far, if you have any questions. Okay. Okay, now we'll move on. So this is value of state value function, right? Now we'll slightly extend this idea, and then finally we'll build Bellman expectation equation. Now, how do you calculate this Q value? Now we'll see. So what we got here, you see? Yeah, right. So what we got value of a status. Now the value of status was expressed using Q value. So the state value function was expressed using action value function, right? So it is q phi of s comma a. Now we'll try to expand this q phi of s comma a. That means what? Your state is fixed, means for in a given state your action is fixed. So from that state onwards, how much reward you will get. So you want to analyze q phi of s comma a, right? Q phi of s comma a. This we want to analyze, right? So how do you get this q phi of s comma a? Q phi of s comma a means what? This is q phi of s comma a, you see, right? So how do you get this q phi of s comma a now? That means what? On a state, your action is fixed. So how do you calculate this q phi of s comma a? So here we introduce one more notion, q phi of s comma a. How do you? That means what? In state S, you have taken an action A. In state S, you have taken some action. State S, you are in state S. You have taken some action A1. So here we introduce one more thing called the probabilistic nature. The probabilistic nature is like this one. Suppose you are at state S. If you take an action A, it is not guaranteed that you will end up in state S1 or you will end up in state S2. So the success state for a given action is not deterministic. It also varies. Varies means what? It is again probabilistic. So why this probabilistic stochastic nature comes into picture? This stochasticity nature comes into picture due to the noise in the environment, or that due to the noise. So what is this noise? Let me give a simple example. Why after taking an action, so that means what? After taking an action, you may end up in S1 with probability 0.5 or 0.9, S2 with probability 0.05, S3 with probability 0.005, and so on, like this. So it is not guaranteed that after taking an action you will end up in S1 or S2 or S3. Again, we have stochastic nature here. So let me give this example to understand this. Suppose you are at your office. You are at your office and it is 5 p.m. in the evening. You want to leave your office. So your action, what is your action? Your action is to leave the office. You want to go your house. So typically what should happen if your action is leave? You should end up in your house, right? But I will show you here that with small probability, you will end up in your office itself again. Why? Let us say you have decided to leave. You went to the parking lot to pick your bike. You went to your parking lot, right? Then you are about to leave, right? You are leaving. Then rain came. Suddenly rain came. You have no umbrella with you. So although your action is to leave, where you ended up? So again, you ended in your office only. Although the probability here is very small, but there is no guarantee that when your action is to leave, you will end up in your house. You may end up in the office with small probability. So this is due to the noise in the environment. So that's why here, suppose your action is A, it is not guaranteed that you will end up in either S1 with 100% probability. With 0.9 you may end up in S1, with 0.05 you may end up in S2, with 0.005 you may end up in S3 also. So now we'll capture this stochastic nature using our mathematical equation. So this stochastic nature was captured by these transition probabilities. These transition probabilities. That means what? Your action is fixed. Your action is fixed. Fixed action. Your current state is fixed. From state S, your action is A. Where will you end up? You may end up in S dash with some probability. You may end up in S double dash with some probability. You may end up in S hat with some probability, and so on. So we have to consider all these probabilities into account while modeling the Q value. Now, so therefore, in a state S, your action is A, right? You will have a reward corresponding to your action, but you may end up in S dash or S double dash or S triple dash and so on. So therefore, what is our Q value? So therefore, the Q value of state S with action A is nothing but, since at state S you have your action is A, you will have a reward corresponding to that action, right? This is called the action reward, right? Reward corresponding to the state action. This is called state action reward. Earlier we have seen something. What is that? RS. This is called the state reward, right? This is the reward corresponding to the state. This is the reward corresponding to state and action. Then after the action, you may end up in some successor state. So for each successor state, let us say S is the set of successor states. So for each successor state, what we do? We take sum over the transition probability S dash. What is the probability that you will end up in S dash? What is the probability that you will end up in S dash after taking an action A, multiplied by value of state S dash following policy phi. So this is how we get the action value function. Now, if you see, this is recursive. The value function was defined with respect to action value function. Then the action value function was defined with respect to, again, state value function. So therefore, if you substitute this equation here, then this becomes this. Can you see? The only change is, instead of Q pi SA, we replace this entire thing. Then this will become this. Is it okay? So this is called the Bellman expectation equation for state value function. So this can be understood using this figure. So from a given state, you will have multiple actions. For a given action, you may end up in multiple states with different probabilities. So these are transition probabilities, whereas this is policy, right? This is policy. This was given by policy, whereas this is uncertain in nature. This is transition probabilities. This, you can say, this is the uncertainty of the environment. This is the uncertainty of the policy. Is it clear? Similarly, you can expand this also, this action value function. So here what we have again state value function here. If you substitute the state value function here, then you can expand this like this, right? So these are the Bellman expectation equations for state value function and action value function. Now using these two state value function and action value functions, we can compute anything here. Now that's why here, if you see here, this, as I said, this is not a state. This is the uncertain nature. That means from this state C3, if your action is pub, you may end up in class 1, or you may end up in class 2, or you may end up in class 3 itself. So what is the probability that you will end up in class 1? 0.2. What is the probability that you will end up in class 2? 0.4. What is the probability that you will end up in class 3? It is again 0.4. So these are the transition probabilities here. Is it clear? So now you see how we calculated the value of this state as 7.4. How we calculated? We calculated based on this formula. So if you see here, what is phi of AS? Phi of AS is 0.5, right? So here if you see, this is 0.5, this is 0.5, but here it is 0, so that's why it got cancelled out, 0.5 into 0, right? Whereas here if you see 0.5 into What is the reward corresponding to this action? What is the reward corresponding to this action? 1. It was given earlier. Where is this? Yeah, here it was written. You see, what is the reward corresponding to the action going to the pub? 1. So this is the 1 here. Then after pub, you may end up in C1, or you may end up in C2, or you may end up in C3. Right. So what is the probability that you will end up in C1? It is 0.2. So 0.2 times, what is the value of C1? Minus 1.3. Similarly, 0.4 times 2.7. 0.4 times 7.4. Is it okay? Then the other 0.5. This is 0.5 times. What is the reward corresponding to the action study? 10. Reward corresponding to the action is 10. And what is the reward corresponding to the success state? 0. That's why it is 0.5 times 10 plus 0 is 10. That's why you got 7.4. Is it clear how we got this? Can someone yeah. Can someone check how we got 2.7 here based on the same analysis? How we got value of C2 as 2.7? Can you write? Value of C2. It is simple. It is not as complicated as that one. How we got value of C2 as 2.7? As I said, the probability of taking an action is 0.5 each action, because there are only 2 actions from C2. Right? Moving up or moving right. Can you post in chat box? What do you got? V, value of state, value of state C2. How we got it as 2.4? You see, if from state C2 you can go to C3, or you can go to this sleep state, right? The probability of taking this action, study or sleep, is 0.5, right? So therefore it is 0.5 times something plus 0.5 times something. What is this first one? Let us say you go to class 3. So when you take this action study, what is the immediate reward that you got? -2. Plus what is the reward of this this state? 7.4. What about the other one, 0.5? When you take this action, sleep, what is the immediate reward? 0. What is the reward of success state? 0. So that means it is 0 plus 0. That means this got this has nothing. So this is 0.5 times 5.4. Right? Is it 5.4? Yeah. So you got 2.7. Is it clear? Similarly, we will get minus 1.3 here, minus 2.3 here, and so on. Right? But now the question is, if you see here, in order to calculate 2.7, you need this. In order to calculate 1.3, you need this. In order to calculate this, you need this, right? Because from here you can come here. Then how do we calculate all this? Right? That is the question. Okay, we calculate 7.4 here, but for this, what do we need? We need this. But since it is a terminal state, we don't know. You see, there are no outgoing transitions. Therefore, the reward, the value from this state is 0. So we start here, then we try to compute. So you see here, it depends on this one. It was not computed, so we leave it. Whereas this one, it only depends on this one. So we compute this first, then we compute this, then we compute this, then we compute this. But again, in order to compute this, we need this. So how to solve this? So this we'll see now. So how to compute? Okay, we have equation, but how do we compute values of each and every state? Because there are dependencies here. So similar to MRP, we can write this Bellman expectation equation like this: V phi equals to R phi plus gamma times P phi of V phi, right? So this P phi is a matrix, V phi is a vector, R phi is a vector, V phi is a vector. So you can compute V phi by computing the inverse. But again, the same problem remains. What is that problem? If the matrix size is large, then computing inverse will take a lot of time, right? So now the question is, how do you compute, right? So we use different methods called policy iteration and value iteration to find out value of each and every state. So now let us move on to something known as optimal value and optimal policy. So what is optimal value? So just now we have seen that these are the values of each and every state, right? So what is the policy here? Can you tell me the policy? So the policy that we have used is a simple policy. The policy that we used is called uniform random policy. It is uniform random policy. What do you mean by this uniform random policy? At any state, you have only two actions, right? In that example, you can see at any state we have at most two actions, either moving up, moving right, moving up, moving right, moving down, staying in the same state, and so on, right? So the uniform random policy basically says that phi of A1 given as phi of A2 given as are equal. They are uniform means what? The probability of picking A1 and probability of picking A2 is same. How many actions are there? Two actions. So therefore the probability of picking each action is 1/2, which is 0.5. So this is kind of uniform random policy, and the corresponding values we have seen just now. We have calculated the values corresponding to this policy, right? Now the question is, okay, these are the values corresponding to some policy, some uniform random policy. But what we want to compute is, we want to compute optimal values of each and every state. So for that, let us define what do you mean by optimal value, right? So optimal value of a state is the maximum value of the state over all policies. That means what? Let me write this one. So that means, so we have different policies. Let us say policy phi 1, policy phi 2, policy phi 1, policy phi 2, policy phi 3, policy phi 4. Let us like this. Let us say you have some 10 policies, 10 different policies. For each policy, you got values. Value of state S1 following policy 1, value of state S2 following policy 1, value of state Sn following policy 1. Similarly, value of state S1 following right? We got values of each and every state following different policies. When do we say that the value is optimal? What is optimal value function? So we say that so if you see here, what is an optimal value of a state? Optimal value of a state is nothing but if you take the maximum over all policies, whatever gives you the maximum, that is called optimal value. Similarly, whatever gives maximum here, that is optimal value, and so on. Is it clear? The maximum value that you will get over all policies. Let us say here 100, here 500, here 300, here 20, and so on. So the optimal value is 500. So that's why if you see here, we take maximum over all policies. Similarly, optimal action value, we take maximum over all policies. So these are the optimal values. These are the optimal values for all the states. All the states. That means what? You explore all possible policies, then find out the maximum value of each and every state. Is it clear? Any questions so far? Similarly, these are the, okay. Is it clear? Okay. Now we'll see this optimal. Okay, if you see now the optimal Q values. Optimal Q values means what? Okay, you see here now. So these are the optimal Q values. But now let us see what do you mean by optimal Q value? Okay, optimal Q values, optimal values. Okay, let me go back. Let me finish this. So if you see, these are the optimal values. That means what? Over all policies, you evaluate each policy for each and every state. So whatever policy gives the maximum value, that is the optimal value. Then what do you mean by optimal action value? Optimal action value means what? From state S, suppose let us take this one. State C1, your action is to study, right? Your action is to study, but here the action is fixed. From here onwards, you have again two actions, either going this or going this, right? So again, different actions will come into picture here. So you have to evaluate all possible policies here. Then you have to calculate the maximum Q value that you get here. So after computing that, you will get that the optimal Q action value here is 6. That means when your action at state C1 is study, then the maximum reward that you will get, maximum cumulative reward that you will get is 6. Is it clear? Any questions? Now the next thing is, what is optimal policy? So whatever policy gives maximum value for each and every state, that is called optimal policy. That means, okay, I have erased, I think. Okay, here. Suppose, let us say 5,4 gives you maximum value for each and every state. That means what? Here you got 700. Here it got 800. Here it got 1100. And the value 700 is maximum among all the policies for this state, maximum among all the policies for this state, and this is maximum among all the policies for this particular state. Then we say that 5,4 is the optimal policy. So optimal policy is the one which gives maximum value for every state. You see, what is optimal policy? Optimal policy is the one which gives maximum value for each and every state. Similarly, it gives maximum action value for each and every state action. So an optimal policy was highlighted here. You see, what is policy? Policy means what is the path you have to follow, right? So here you can see that the optimal policy was highlighted with red. That means what? From C1, what should be the action? The action from C1 is to go to class C2. From C2, what is the best action? The best action is to move to C3. From C3, what is the best action? From C3, the best action is to go to this particular state, right? Similarly, from this Facebook state, what is the best action? The best action is to go to class C1. Is it clear? So this is kind of deterministic policy. There is no probability here. This is a deterministic policy. Any questions so far? If you have any questions, I'll take. Any questions? If you have any questions, please post in chat box.
Sir, can you relate all these things with the real life application? Any example for we are having different policies and we are having different reward values?
Okay.
Huh.
So let me open one more. Real life application means okay. Okay. So suppose let us assume that okay, networks is not better. Okay, suppose robotics is better, or I'm thinking what to. Okay, suppose you take a robot. You have thrown the robot in an environment which is new to the robot. Robot is not aware of this environment actually, right? So now this robot has to reach some point. Let us say some goal. This is the target it has to reach, right? It doesn't know anything about the environment, and it doesn't know that this is the goal. It doesn't know anything. Finally, what we wanted to train this robot is, we want to train this robot to reach this point. Let us say this robot, okay, otherwise yeah, okay, otherwise let me give one more example rather than this, then that will be better. So suppose you have some autonomous car, right? You have an autonomous car, autonomous vehicle. You want this autonomous in future. Suppose you want to train this car such that this car has to pick the passengers from some location, and it has to drop the passengers at some other locations, let us say. Now it don't know what is the pickup location, what is the drop location, right? Now it will move here and there, and finally it has to go to this pickup location. And similarly, suppose let us say the pickup locations are these two, and these are the drop locations, right? So either the passenger will be here or here, then this car has to go and pick the passenger, and it has to drop here. Now it has to deliver the passenger. It has to deliver the passenger. Let us say in minimum number of steps, minimum route. Let us take this simple example. In minimum number of steps, this car has to deliver the passenger at this dropping location. But this environment is not known to this car. So what it will do, it will try to explore, right? So every time when it moves, then it will get a feedback. The feedback is kind of reward. What is the reward? Reward may be something, some number, either positive number or negative number, something, right? So reward may be like distance, let us say, how far it is from this destination or dropping location. Let us say if it go here, how far it is from the dropping location? Let us say 50 km. If it goes here, let us say it is 45 km. If it comes here, let us say it is from 30 km from the, so it is numbers, nothing called km, right? This is kind of feedback. So feedback, so since the distance is 30 km from the drop location, we give high reward for this. That means we give 100 here. Since it is 50, we give less reward here. Let us say 50 here. Let us say 60 here, right? So the goal of the agent is to maximize this cumulative reward. So initially what it will do is it will interact. It will go here and there. Then from here it will move in different actions. So while moving, it will try to accumulate reward. Do you agree? It will try to accumulate.
Sir,
Yeah.
one question. In the previous example, as you had stated that if the student is attending the class, the
Yeah.
reward will be in negative, right?
No. Yeah.
And if he is sleeping, then the reward will be 0. And if it is using the Facebook, then again reward is some negative because it is consuming the energy. So
Yeah.
as the energy is consumed, the reward will be goes negatively.
Hmm.
And if the student pass, then the reward will be positive, right?
Yeah. That
So
example.
that is the logic you had used here, that if it is 50 kilometer, then the reward is only 50.
No. You see here, we want the robot. Please. We want the robot to reach the destination in minimum number of steps. Right?
Okay.
Quickly, it has to reach quickly.
So reward depends on our objective, sir?
Yeah, our reward depends on our objective. We have to fix how to give reward.
Okay, sir. Okay.
Yeah, reward is not predefined. The user, whoever is designing the system has to fix the rewards accordingly.
Okay, sir.
Okay, so if you have any other questions, I'll take. Any questions?
No, sir. No.
Okay, I'll share the slides with Dr. Sanjay sir. If you have any questions, I'll take now. You can post in chat box. Otherwise, I'll close the session here.
Thank you,
Thank
sir.
you, Vala sir.
Thank you, sir.
Okay, sir. Thank you.
Thank you very much, Bala Prakash sir. Nice presentation, and it will be very helpful